Oh, yeah. Okay, page 1. Let's go down and look at number 3. Now, as a quick review of what mean value theorem is, this is also on page 3 of your packet. The idea is that if we have endpoints, from the endpoints, we can find the slope between those 2 points, which is f of b minus f of a over b minus a. That's just finding your slope value. And then you're going to take that slope. You're going to also find the derivative function and then set them equal to each other. When that happens, you can figure out where else on this curve is this slope exists. So if there's a slope of 1/2 between the 2 endpoints, then we know there must be a slope of 1/2 somewhere along the curve. And when we set the derivative equal to that average slope, we can solve for x and we can find the location of that particular steepness. Again, we have 2 conditions for mean value theorem. Is the function continuous on the closed interval? Is it differentiable in the open interval? And then we go about finding all the information that we can, eventually working towards solving for x. There. So we'll skip 1 and 2 here. Let's go to number 3. Determine whether mean value theorem applies for the function sine of 2x plus x on the interval from 0 to 2 pi. If so, find the values of c defined on the interval, defined in the theorem. Okay? If not, state the reason why. Well, the nice thing is that with sine functions, there are no sharp turns. There are no asymptotes. So our first 2 conditions will pass. We just have to make sure we state those 2 conditions. Okay, so we know our function is continuous on the closed interval, so bracket from 0 to 2 pi. And our function is also differentiable on the open interval. So f of x is differentiable parentheses 0 to 2 pi. Okay, and we know that without having to do any work because we know the sine graph is just nice and continuous. There are no asymptotes, there are no holes, there are no sharp turns. Okay, so this is our goal. Our goal is to eventually go through this formula. Okay, so this is a 2-step process here. We're not going to be able to do all this in 1 step. The 2 things that we need to do is we have to find the slope between the endpoints. And then secondly, we'll need to find the derivative. And then once we have those 2 information, we can set them equal to each other and then solve for x. Okay, let's do the more tedious part. That's just finding the slope between the endpoints. We're going to take those 2 endpoints, plug it into the function, get those y values, get those order pairs. All right. So my function is sine of 2x plus x. We have our endpoints provided, so we'll need to find f of 0. We need to find f of 2 pi. What's sine of 0 plus 0? Just what? 0, okay. F of 2 pi. So I plug 2 into x. Sine of 4 pi, what's sine of 4 pi? Sine of 4 pi is same thing as sine of 2 pi, which is same thing as sine of 0. They're all going to be equal to what? Yeah, 0 plus 2 pi. Okay, so 0 plus 2 pi will be 2 pi. Yes, question?
Never mind.
All right, so now that we have order pairs, what are we going to do with this information? Find the slope. Yeah. Change in y over the change in x. So we're taking care of this portion first, and then we can move on to the derivative. Or I can call this average rate of change. Okay, whatever we want to call it. So change in y over change in x. All right, so what slope are we trying to look for? Slope of what? Slope of 1. Yeah. So we know that there, between the two endpoints, this graph has a slope of 1, but we want to look for, okay, maybe the graph looks like this. Right. Between the endpoints, there's a slope of 1, but we want to know where on the curve is there a slope of 1. That's what mean value theorem is going to do for us. It's going to help us find that location on the curve where there's also the steepness of 1. We know there's a slope of 1 somewhere. We're just going to look for it. Okay, so now we have this piece. Okay, we know what our goal is. Now we need to find the what? Find the derivative. Yeah. So our function is sine of 2x plus x. F prime of x is equal to sine of u becomes what? Yeah, cosine of u times u prime. So cosine of 2x times 2 plus 1. Let me clean this up here. Okay, so now we have the pieces that we need that we want to set equal to each other. We have our derivative. We have our average rate of change. We'll do it with this information. Set them equal, right? We have our derivative. We have our slope. We're going to set them equal. Sorry?
Why did you do plus?
Oh, we did plus 1 because x's derivative is 1. So we're just taking each term's derivative.
Oh,
What's going to happen with the ones? Cancel out, right? I'm going to end up with 0, divide both sides by 2, and I'm just left with cosine of 2x is equal to 0. Okay, we want to solve for x. I mean, we could do guess and check to figure out what this is, but I think maybe the cleaner way is we'll do inverse trig here. This will just allow us to get x by itself, and then we'll solve for x. So we can always move our cosine to the other side. We got to call it inverse though. So right now I just want to figure out how can I get x by itself. So 2x is equal to inverse cosine of 0. From here, we can find all the list of radian measures where cosine of theta is equal to 0. So if you think about inverse, or think about where cosine theta is equal to 0, what theta values can you think of? Cosine of what is equal to 0? Pi over 2. Where else? 3 pi over 2, right? Now, what I'm going to do is I'm going to go a little further beyond the initial 0 to pi, because eventually that x is going to shrink, and when they shrink, we want to ultimately have all the values between 0 and 2 pi. So because they're shrinking, I'm going to go a little further out past 2 pi. So I can find coterminal angles by adding what to these two values at 2 pi, right? So pi over 2 plus 4 pi over 2 is 5 pi over 2. I want to just go maybe beyond what I think I need, because eventually all these values are going to shrink, and I want to find all the values between 0 and 2 pi. So 3 pi over 2 plus 2 pi, that's the same thing as 3 pi over 2 plus 4 pi over 2. That's 7 pi over 2. That should be enough. But if I want to go further, I can go 9 pi over 2. Okay, so now I want to solve for x. I know all those values will shrink because I'm going to divide everything by 2, which is the same thing as multiplying by what? 1/2. Okay, so the distribute the 1/2 through, and I get x is equal to pi over, what's the first one? Pi over 4. Yep, and everything is every denominator. Say it again.
Denies extraneous to it. If he's
Yeah, I think so. So let's see, 5 pi over 4, 9 pi over 4. Sorry, 7 pi over 4, and 9 pi over 4. Yeah, 9 pi over 4 is past the 2 pi mark, so we know this. I like to go past so that it just gives me confirmation that I didn't miss anything, that I caught everything that I need. So these are all the locations on the graph where this curve is going to hit a slope of 1. So it's going to continually hit all these locations on the graph. The graph is going to hit a slope of 1.
your final.
Those are my C values. Yeah.
You
So
know,
basically, yeah. Go
I
ahead.
never graphing units.
No. Yeah. But if you wanted to, you could also put this in the calculator and just visually see for yourself that your graph is going to experience a slope of 1 4 times. Right, by something here, 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 and here. All right, so you'll see a mean valley theorem or Rolle's theorem on the test. Now, Rolle's theorem is basically the same thing. It's just when you find the slope between the endpoints, your 2 y values will be the same. And then if you subtract the same 2 y values, you're going to get 0. So you're always going to be setting f prime equal to 0 for Rolle's theorem. For mean valley theorem, you're setting the derivative equal to a slope that could be other than 0, most likely other than 0. That's the difference. Okay. All right, so we're just going to do more curve sketching today. So let's turn to page 10. And we'll do another trig function here. So not page 10. Page 10 is the key. Page 8. And if you feel like you need additional space, feel free to come up and grab a scratch sheet from one of my shelves. Okay, we like to start off by graphing just to see what we have in front of us, and then we can always use our calculator to confirm all the answers that we're getting. So if you have a calculator here, let's go ahead and practice typing that in. Again, make sure that you're in radian mode. Always use x as your variable, even if the paper tells you a different variable. You can do zoom 6. Now notice your domain here is from negative pi to pi, which you can say, you can type in negative pi to pi under your, if you go to window. Remember, you're only playing with 4 numbers. If you want to adjust these numbers by hand, you're only playing with x min, x max, and y min, y max. Do not try to play with any other numbers. Okay. So if you want, you can go from negative pi to pi. If you want, pi is that caret button there, second caret. But if you want to see a little bit past those edges there, I can go from -4 to 4. A graph. Now, if you feel like this is pretty good, but if you feel like you want this to take up more of, if you want to fill in these empty spaces, you can adjust your window so that your y values aren't going up as high or as low. So if you want to adjust it to from -5 to 5 or from -6 to 6, again, I just want to have you guys play around with those 4 numbers so that you feel comfortable knowing what the graph is going to do, right? If something doesn't, if you wanted to tailor it to something that you want to have a closer look at the graph, then maybe this can do it from -6 to 6. I can probably even go less than that, maybe from like -3 to 3 or -4 to 4. But this is pretty good. This is pretty much going to be what our graph is going to look like after everything is said and done. All right, so let's go to our work for showing. Okay, so let's find y prime. First derivative test, and then test for concavity. Gather all of our information, and then being able to write our intervals of increase, decrease, and everything else. Okay. All right, 2 sine x becomes 2 cosine x. 2 cosine x becomes negative, yeah. All right, to find critical points, we set f prime or y prime equal to 0. Okay. There's no GCF that we can do, but here's a trick that we can, not trick, but this is something that we can help you see, especially if you're dealing with cosine and sine. What if we move that 2 sine over to the other side here? 2 sine of x is equal to 2 cosine of x. All right, the 2's cancel out. Sine of x equals cosine of x. So if we think about your unit circle value, where is your sine and cosine equal to each other? In the family of what? Power 4, right? So you know that, which is fine. That this is enough for you to help find what you're looking for. Another way that you can do this is you can divide both sides by cosine. We're not dividing the cosine away, we're just creating a different version of it. And if I divide sine over cosine, what is that equal to? Tangent. Tangent of x is equal to 1. Same thing, right? Power 4 family. If you want to, you don't have to go down to this step. If you feel comfortable knowing, okay, I'm just looking for where sine is equal to cosine, it's going to be either in the first or third quadrant, right? They're both either positive or both negative. You can also get that conclusion by looking at tangent, right? So tangent is going to be equal to 1 at power 4 and what? Yeah, power 4 by power 4. But are both of these inside our interval? Power 4 is good, but 5 power 4 is outside, right? We're just going past that pi. So what can we do to find a different variation of this? Subtract what? 2 pi, yeah. So if something doesn't fit, you can always add or subtract 2 pi to see if you can get it to fit in that interval. So subtracting 2 pi is the same thing as saying minus 8 pi over 4. Okay, so now these both fit, and we're going to use these two as what goes onto our slope sine line. Okay, we already know what the graph is going to look like, but I still want to see that if you can just show me that you're testing one interval, and then once you find that, you know the others will be alternating in sign. So pick the easiest one for you to test. Maybe I'll test 0 because 0 lands nicely between -3 power 4 and power 4. Where do I plug 0 into? Into a derivative, right? Okay. All right, so 0 for x. 2 cosine of 0 minus 2 sine of 0. Is that positive or negative? Cosine of 0 is 1, right? 1 times 2 is 2. Sine of 0 is 0. So 2 minus 0 is positive. So I know that in this interval, my graph is going to have what? What slope? Positive slope. And I know my sine is going to alternate. So, I mean, I can test other points here as well, but I know both of these will be decreasing. And that should be consistent with what we see in our graph here, right? Decreasing, increasing, decreasing. All right, what do you expect at -3 power 4? Relative min. What do you expect at power 4? Relative max. Okay, so let's find the exact values, and then we can use our calculator to find those approximations for our graph. Okay, now if I want to find relative max, relative min, where do I take these x values, put them into the original, right? So I want to see exact value. If you're plugging this in the calculator and you're getting me a decimal value, you'll get some points, but you won't get the full credit, right? I want to see that you're using your unit circle values to get it down to an exact numeric expression. Back into the original function. Now, if you don't recognize -3 power 4, it's okay. Just look back at where it came from. It's basically coming from 5 power 4. So we can just pretend like it's 5 power 4 here, right? So what's sine of 5 power 4? Third quadrant. So in that, yeah, in that power 4 family, right? So 2 times -√2 over 2. Okay, what's cosine of 5 power 4? Also √2 over 2, yeah. All right, so to clean this up, it looks like the 2's can cancel out. -√2 minus √2 is what? -2 √2, right? Adding like terms there. There's one of them here. There's -1 is -2. Right, so we have an ordered pair for the relative minimum. And, we can use the calculator to help us get an approximation of that so that we have an idea where to graph that point. But on paper, this is what I'm looking for. I want to see that you can get it down to that number, even if you're using your calculator to approximate it for your graph. Okay, same thing, pi over 4. Let's find our relative max. This feels easier, right? Where everything's in the first quadrant here. Both are positive. Twos cancel out, so √2 plus √2 is 2√2. That's our relative max. Okay, we'll fill in all those min and max later. Let's just get the messy stuff out of the way. Let's find the second derivative function, create a second derivative sine line, do our test for concavity. Okay. Okay, so here's f prime. F prime is 2 cosine x minus 2 sine x. Let's find the second derivative. Cosine x becomes negative, okay, negative 2 sine of x. And then sine x, 2 sine x becomes cosine. The negative doesn't change, right? That negative will stay there. Right, set equal to 0. Yeah. Looks like now I'm looking for where sine and cosine are opposite signs. So, but whether they're still the same. But I can also do this. I can divide both sides by you want to see a different variation of it. Basically, now we're looking for where is tangent equal to -1. So which quadrants will that be? 2 and 4, right? Yeah. So it's also where sine and cosine are going to share the same numeric value, but be opposite signs. So we can say x is 3 pi over 4. Sorry. And 7 pi over. But our interval is from -pi to pi, so which one do we have to adjust? Yeah, the 7 pi over 4. So what can we do with that? Subtract 3 pi, yeah. Okay, place these two onto my second derivative sine line. Now I'm looking for intervals of concave up and concave down. The problems I give you will always alternate in predictable ways. So let's just find one concavity by hand, and we can figure out the rest because we know what the pattern is going to be. So let's test 0. Plug 0 into the second derivative. So 0 in for x, -2 sine of 0, that's going to be 0. -2 cosine of 0, that's going to be -2 times 1, which is -2. This is concave what? Negative, so concave down, which means the others will be opposite signs. At least the ones I gave you. What do you expect out of these 2 points? These are both what? Points of inflection. How can I find those y values? Into the original. Yeah, back to the original. Okay, so I want to see you being able to find those values by hand. You can use your calculator to double check your decimal value, but I want to see exact values for full credit. All right. Use sine of x. Okay, if you don't recognize -pi over 4, just think about where it came from. It came from 7 pi over 4. What's sine of 7 pi over 4? Negative, yeah. Okay, so -2. All right, what's cosine of 7 pi over 4? That'll be a positive, right? Okay. What's that going to give me?
0.
0, yeah. So 2 cancel out. I'm left with -√2 plus √2. That's going to be equal to 0. So that's my order pair. Let's find the other order pair for my other point of inflection. All right, what's sine of 3 pi over 4? Second quadrant sine is going to be positive, right? And then what about cosine of 3 pi over 4? Negative, yeah. So this is also going to give me what? 0, yeah. All right, so we have all the order pairs that we need. Okay, let's now see if we can build our graph. So the only other order pairs that I want besides points of inflection and relative max, relative min are the endpoints. So we're also going to plot the endpoints into the original function, get those y values, and obviously you can use your calculator to check all of this work here, but I'm going to go to my graph here. I want to find my order pairs of the endpoints. Now, negative pi is same thing as pi, right? If I add 2 pi to this, so sine of pi is going to be 0. Cosine of pi is going to be negative 1. So 0 minus 2 is negative 2. Same result here, right? Sine of pi is 0. Cosine of pi is negative 1. Negative 1 times 2 is negative 2. Okay, so I have my endpoints. I have my relative max. I have my relative min. I have my points of inflection. Let's see if we can put them all onto our graph here. You plug in the calculator, negative 2 root 2 is around negative 2 point something. Negative 2.8. So we know at negative 3 pi over 4, we know we're going to be expecting a relative minimum. At pi over 4, we're expecting a relative max at 2 root 2, y value 2 root 2. At negative pi over 4 is our point of inflection. We know our y value is 0. At 3 pi over 4, y value is 0 as well. So we know our graph is going to follow this behavior. Going to start off decreasing, hit my relative minimum, increase, hit my relative max, decrease after that. And my graph is going to experience first concave up, hit my point of inflection, concave down, hit my point of inflection, concave up. So now I'm going to retrace my graph with the exaggerated concavity here. So up to this point, I know I'm expecting concave up. Between the next 2 points of inflections, I know my graph's going to shift to concave down and then back to concave up. Okay, so let's practice writing out all of our because statements. And really the only thing that we need are our sign lines, right? We know our intervals of decrease. We know our intervals of increase. We know where our relative max is. We know our relative min is. We know our intervals of concave up. We know our intervals of concave down. We know our points of inflection. So from memory, see if you can recall all the because statements that goes with all these intervals and max and min. Okay, so go ahead and try that, and then I'll put the key up, but you can also check the key yourself on page 10. Okay, so we'll do that for our remaining 5 to 10 minutes, yeah, and then we'll check our answers. Okay. Let me know if you have any questions. You're writing your statements.
I think you put a bracket on the like negative pi and on the pi side on decreasing till it goes to anything.
I'm always going to use parentheses, but I think College Board will be okay with brackets as well. The idea is, my idea with parentheses is that after this point is no longer increasing, is no longer decreasing because it actually hits the relative minimum. So I always use parentheses for all my intervals. But just understand that the relative max, relative min, these are not intervals. These are actually order pairs. That's the x, that's the y value. So I know the notation looks the same, but this isn't, these are x values. This is the x and the y value. Okay, hopefully after the second day of doing curve sketching, it feels more comfortable. But I mean, we still have all next week to practice this process. So and it's also nice to have a calculator to kind of back up all the work that you're doing, confirming it. So okay, so tomorrow we're going to do related rates. Okay, I'll get you guys. No homework tonight.
Everyone's gonna does the list, just 31.
Yeah, it's one of these. one related rate, one curve sketching, one mean value theorem, one with, yeah.
Yeah. It's.
You won't have any problem like the quiz, but you do need knowledge from the quiz.
You just don't memorize the identity. Sorry. It really relates to like what we were doing before, but like now.
Yeah, but now we're true, right? So everything's something from a right triangle perspective.
So no, like home problems or something. Is there any like Pythagorean theorem involved in that?
Yes, the Pythagorean theorem. We can also build in the Pythagorean theorem into as parts B or C of a trig problem. So you'll still see ladder problem, something like that.
Okay.
That's as far as we're gonna get.
Eagle Scout board reviews tonight.
Oh, okay, good luck.
Thank you.
Yeah.
I passed them Eagle Scouts, so I'm really hoping.
You think, is it pretty much a done deal or is it pretty
Like they pretty much like, there's no guarantee for it, still have to try your best, but it's like, they pretty much are gonna give it to you unless like you like really mess up or you
Right.
think you didn't deserve it. Right. So it's like,
That's good.
as long as you keep like, you know, not answers like the best of your ability.
Good.
Like you didn't, you don't have any merit badges or anything.
Right. You've already shown all your work, so.
Yeah.
That's good.
Eagle Project was the hardest part. Kind of like a reflection a little bit.
Yeah.
You and Scouts.
But, I mean, you learn a lot, right?
Oh, yeah.
That process.
It's good for like, you know, future like colleges.
Mhm.